So, hello everybody. I'm Biagio Cosenza from Technische University of Berlin, and this is a joint work with the University of Stanford and the University of Innsbruck. If you didn't understand what is the topic about from the title, this is about applying machine learning to compilers. So, but it's not the usual machine learning model. It's not deep learning. Because the context is very different here. We have very little data, and therefore we need to design very smart model. So we really have to design machine learning model that adapts to the problem. And so this work is about designing machine learning model that adapts to compiler context. In this case, a compiler for Stencil Computation. I will show you what is a Stencil Computation and explain how we translated this, we build a machine learning model to solve this problem, and explain the novelties of our approach. So this structural learning formulation that really adapts very well to this kind of problem. And in the end, I will show you just few experimental results. I will not bother you with all the results we got. If you want to know the details and the implementation details, we had a paper in IPDPS this year showing the whole approach. So Stencil Computation, if you don't know what it's about, actually image processing kernel, partial differential equation, Jacobi kernel, they are all Stencil Computation. And they are usually something like that. So we have an outer loop which iterate for each time step. Then we usually iterate over, for instance, a grid. So we iterate for each cell of a grid, but this applies also to two-dimensional case with pictures. No? We iterate for all the pixels. And then what we do is, according to the common definition of Stencil Computation, we have one write, we update one element. But to calculate how to update this element, we read what we call a stencil shape or a stencil pattern, which is static. And it's about a number of neighbor elements in the grid we read in order to calculate the element to write. We can also read from different time step, but this is for instance, is a 6-point von Neumann stencil. We can have a different shape depending on the problem, but overall, this is how a Stencil Computation is, and it is usually a memory-bounded problem. Now, it is a very interesting problem, well studied because you find it everywhere, and for that, there are specific compilers working only for this kind of pattern. One is the one I used to base my work, is the Pathos Stencil Compiler. More information in this publication from Kristen. And for instance, this compiler is the one I use. They optimize this code first by applying blocking in the free loop. So we have three-dimensional blocking, tiling. Then it applies unrolling in the innermost loop, which also works very well. And finally, it does both multi-threading and SIMD, and it uses SIMD instruction. And those are the transformation exposed. And all of those transformations, they expose some tunable parameters. So you have, for instance, free value for the blocking, because you have the blocking size is a three-dimensional value. Unrolling factors for unrolling, you can just don't do any rolling. You can do a rolling of 2, 4, and in the case of multi-threading and SIMD, you can decide how much work to give for each thread, and I will call I use the same terminology of Kristen's. I will call it chunk. So the chunking factor. So the amount of work we give to each thread. This is very important for performance, to balance memory with computation. So overall, if we consider all the possible transformation, we have about 60,000 possible transformation for a stencil code. And the problem is not just that we have a rather large transformation space. The problem is that this space is has discontinuities. It's not so easy to model. And that's why stencil computation is a known problem for automatic tuning. So we need to tune our transformation, and we would like to do it automatically. This is a great challenge. So there are many other problems where we apply automatic tuning. One is, for instance, tuning GCC compiler flag. This is a very known test benchmark. And we actually use machine learning to solve this problem. Think about that the standard approach to find a good solution, a good tuning for this problem, state of the art, is to use iterative search. So you have one code, you try a combination, then you try another one, then try another one by using search heuristics. And after hours, you will finally find a good configuration. The problem is of this approach, it takes a lot of time, and if you have, like in our case, you have multiple codes, there is no way to share your knowledge. So the idea while using machine learning in compilers is that you move the complexity in a pre-processing stage. What you do is to have many codes, try many configurations, build a machine learning model, and then when you deploy this in a compiler and you have a new unseen code, you just query the model, which means look for similarities in the code you have seen, and then you get your optimal solution, optimal according to your model. Of course, the search space is very big. We will never know if we really get the optimal, because this means to do brute force, and here it's not doable. So this is the general approach of using machine learning compiler. In this context, what we do is to use structural learning. It's not neural network. Actually, we use a structural formulation of support vector machine. And the idea is that, well, this is not just another classification problem or another regression problem. This is a problem with a well-known structure, and we want to exploit the structure in the machine learning formulation. Therefore, using a machine learning approach that is specifically designed for automatic tuning. I will show you. So this implies that we have to take those stencil code, encode those codes somewhat in a feature representation, build a model using a structural formulation, and in the end, when we have a new unseen code, we just query the model we created. First step is stencil encoding. This is rather simple. Actually, the stencil shape is translated in a vector representation of 0 and 1s. We use a sparse vector representation for efficiency. And we also encode other features like the input size, the number of buffer, the type, because we use both float and double. This is very important for memory, for the memory impact. So we have, of course, a way to translate both the stencil code, so the static part, and the runtime parameters into a vector. And this is a requirement to any machine learning modeling. A very important problem is to get the code, because this is a big problem in general with compiler. You never have enough code. We cannot use deep learning because we don't have all this data. It's not like in image processing, you download your terabyte of data set of picture already labeled. No, you don't have it. And in general, we don't like approach that takes too long time for preprocessing, because we build a new model for each hardware, and it's not really feasible that every time you get a new hardware, you have to do a long training. So we have little data, and we try to have more data by generating the training code automatically. So we have a code generator that what it does is to randomly create code with different shapes like line or hyperplane or Laplacian stencil. Those are typical stencil pattern. Those codes are created with different shapes, with different number of buffer, different buffer type, and executed with different input sides, which is very important because when the size is small, maybe you're not hitting the L2 cache bound, but then the best configuration may change. And different tuning parameters. And for tuning parameters, I mean the optimization we saw before. So we really created the training data in this way. But okay, now we have the data, still not really a large training data set, but we have some data. But how do we model this with machine learning? So say, typical approach, I think if you know machine learning, you know what is classification or regression. But those two approaches have some problem in the context of stencil computation. So classification usually means you have classes. Each class is a transformation. If we only had loop unrolling, it would work. We have only few classes because we only have few unrolling factors. But here we have 40,000 configuration, which means 40,000 classes, and we don't have enough data to cover all the classes. So classification here doesn't work. On the other side, we may use normal regression. But normal regression in this context means performance prediction, which is a much harder problem than the one we have. Our problem is over 40,000 configuration to pick up the best one. I don't want to know the performance. I don't want to predict the performance. And therefore, I can build a model with an higher capacity, with a much better model, if I can just encode this information in the model. The idea is to use what is called ordinal regression. We are looking to predict what I call a ranking function, that it takes those 14 configurations, sorted out, and it's able to say this is the best, the one with the best performance. So this is the general approach. So, and this is a kind of machine learning. This is the first time it's been used into compiler. Actually, it's not even very known. I think it has been used only once by Torsay Hakim from Cornell to classify, to order. When you do a search on Google, you have 10 links, and by using click-through data, you can sort those 10 links. So this is the only time this approach was used, and there are many similarities between those two problems. Just to emphasize the approach, on classification, you have your samples, and what you do is to look for an hyperplane to split those samples in classes. We are looking for an ordering of those samples. So we are doing something differently. And what we will do while building this model is also to compare ranking function to see and to finally find out the one that respects the data in the training set. So this is an example of training set. So what we get when we do the training, we have different code. Each code is executed with different sides, and each one with different tuning configuration. And the idea is that we have the runtime for each of them, but we also have the rank. So we know which one is the best one, number 2, and so forth. In normal regression, you would encode those information, the runtime. We instead encode in the problem only the ranking, which means that we actually encode inequalities in our model. So we encode the information that the first configuration is faster than the second, that is faster than the third. And we generate 2 inequalities for this case. So practically, we have inequalities generated by the ranking, and we encode inequalities in the model. So this is the idea ranking works. So general idea, we have a real ranking we observe in the training data set. We want to build a ranking function that behaves like this real ranking. And how can we understand if this is good or not? Well, we can use, let's assume to have a tau function, and I will tell you what is this tau function later. And this is a function that says, it takes as an input 2 ranking and say, okay, those 2 rankings are similar or are very different. So this is something new, something very specific to this approach. You don't have in classical machine learning approach. We need a way to understand if our approach is good, and this way is by using a tau function. And for the implementation of this approach, we we implemented this as with a structural support vector machine. I used this approach implemented by Joachim in 2002, and this is mainly a support vector machine, so an optimization problem with weight vector. There are actually some differences with respect of support vector machine. For instance, we have to normalize the trade-off, the constant, the parameter C, which is the trade-off between margin size and training error over the number of inequality of the model. But the important thing is that we have our constraint, and those constraints are actually the inequalities generated by the ranking, and they all belong to this P set. One more important detail, but I will not show you the details about the equation that are very boring, but the inequalities, so we don't have a real global ordering of all the configuration, because we cannot compare the configuration that belongs to different code and different input sides. So we actually have a partial ordered training set, and this is a detail that is very important to have it working, because we only had in the model information that are useful for the final ranking. We don't have for this information about a stencil on a big kernel running faster than one on a small kernel, because this is a trivial information. It doesn't improve the capacity of the model, and we are encoding our model in a way that we are really focusing on getting the best from our data. So how does it work? So if you have seen other machine learning application to compilers, there is a training phase. We do our training code generator. The code goes through, so it generates stencil codes. It is a source-to-source compiler, so we have 2 compilation steps. And in the end, we have a multi-versioned binaries, which are executed with different optimization parameters, and we fill out the training data set. Then we do our training set preprocessing. Actually, the preprocessing is very fast, because support vector machine with the linear kernel are super fast, and we build our model. When we deploy this in a compiler, and when we have a new stencil code, and this is the DSL we use a domain-specific language for stencil, we compile it, we extract those code features from the new code, and we compare, we actually do a model inference with the model we have previously built, and we get, practically, when we do this, when we query the model, we query the model with 14,000 configurations. But the model, and this is very quickly on doing that, it takes less than 1 millisecond, sort those configurations out, and what I do is to take the top ranked configuration, and this is my solution. So it is very, in the end, it's not that hard, and you just have to get the top ranked configuration. Just a few words how we understood if the model was working. So actually, we took as a reference state-of-the-art a set of iterative compilation approach based on search heuristics. And here, so search heuristics takes 1024 iteration, which means from minutes to hours, depending on the kernel, in order to reach a very good configuration. And the red line you see there, red, yellow, and orange, those are all different configurations of our model. So we really reach very good performance. This is one code from the IPDPS paper, but an important point, we do it in 1 millisecond, while state-of-the-art approach does it with minutes to hours of compilation time. So this is the great novelty. In general, so what is very interesting of this approach is that we need only 8,000 point dataset. With 8,000 point dataset, which is very small, 15 out of 17 stencil test benchmark are very close to our good solution obtained after hours of iterative search. So this is a very important result. And it's also portable because you can just build a new model on, for instance, I'm now building one for ARM compiler, and it works very well. I just had to implement the Neon backend. The model really you have to change nothing. So this I will skip, but just give you an idea. There is another interesting thing is that we can also evaluate how good is our model in doing the ranking. So not just taking the top ranked, but the whole configuration. To do that, we used what is called Kindle Style, which is a statistical tool. And you can see small model. So Kendall Style has a value between -1 and 1. 1 means the ranking is very good. -1 means that the ranking is not good, actually is bad. So those are two examples of Kendall Style value over the training data set. Very small data set, you see the Kendall Style value are not really good. Just a little larger data set and Kendall Style value are all positive. Here is an overview of how the Kendall Style improves with the increase of the training set, but still a very small training data set. So to conclude, I show you an approach called Ordinal Regression, which is a novel way to use machine learning for compilers. I use this for Stencil Computation, but you can apply it to really very different contexts. Stencil Computation is a very good test benchmark because it's a known automatic tuning test benchmark, but you can apply this also in other contexts. It works with a very small training data set. And actually what is also interesting is that if you have a bit more points in your training data set, it increases the capability of the model to do a correct rank. And as it has a very little training time, so it suits very well the compiler test case. Thank you very much for your attention. If you want to know more about the test, please ask me or have a look to the IPDPS paper.